Hello everyone and welcome you all in the third problem solving class of the course Principles of Signal and System. I am Vivek Kumar Srivastava, a PMRF research scholar of Antenna and Microwave Research Laboratory, Indian Institute of Technology, Roper, and TA of this course. I welcome you all in the today's class and hope this class will be very informative to you. So the in the previous class we have seen system and its classification, where we have seen different kinds of systems such as linear and non-linear system, time variant and time invariant system, system with memory and without memory, then causal, non-causal, and stable and unstable system. So all those topics we have already covered in the previous class. So the agenda of today's class is to cover the basic of linear time invariant system. Then we will jump to impulse response, followed by convolution, and at last we will see linearity, causality, stability criteria of linear time invariant system. So before moving ahead, let me switch off my camera so as to save some bandwidth. So just a minute. Yeah. So yeah, so before moving ahead, there are some problems that student asked in the previous class. So due to time constraint and all, I was unable to answer it. So in the today's class, first of all, we will see the numerical, see the doubts that student asked in the previous class, and then we will jump to the today topic of today's lecture. Okay, so in the previous class, a student has doubt like uh, the integral system, whether it's a Bibo stable or not. So as I said earlier, like in the previous class, that integral operator is basically a unstable system. However, in the previous class, a student has some doubt like why it is a unstable system, because if input applied to this integral operator is finite, then how it becomes this system becomes Bibo unstable. Okay, so uh, let us see that what we done in the previous class. So for our convenience, I assume there that x of tau is equals to u of tau, means it is a unit step signal. Okay, so this is a unit step signal which is basically input to this system, which is basically a integral system. Okay, so at the input I am applying this unit step signal, and at the output what we will get, so at the output we will get triangular input, sorry, triangular response. Okay, so like here is my input signal which is u of n. Okay, sorry, u of tau. This should not be n, this should be tau, because it's a continuous time signal. Okay, so this will be tau, and here is the tau parameter. So at the output what we will get, this is basically y of tau. So at the output what we will get, at the output we will get y of tau is equals to t into u of tau. Okay, so now here we can see that for each tau, for each value of tau, the amplitude of this input signal will be 1. Okay, means it's a it's a bounded input for irrespective of tau, value of tau, means at t tau is equals to 0, its value will be 1. At tau is equals to some other point, that is tau 1, its value will be 1. Whereas at tau is equals to infinite, its value will always be 1, means it's a bounded input. Whereas the output here, if we see, so like at tau is equals to 0, its value is 0, so it's a bounded output. At tau is equals to some other point, that is tau 1, its value will be finite only. Okay, but what happen is, if suppose we are considering tau is equals to infinite, so in this case the value that obtained at the output will be infinite. So y of tau becomes infinite here. It means that for a finite input, what we will achieve at the output, it's a unbounded output. Okay, so that's why this system is Bibo unstable. Okay, so here if we apply input to be bounded, so what we will get at the output, it is unbounded. So that's why this integral operator is basically a Bibo unstable system. Okay, so if audience has any doubt, then please ask. So any doubt in this question, like solution, whatever I provided, if you have any doubt, then please ask. Okay, thanks. So let us move to the next problem. So like one audience in the previous class demands that we have to check whether accumulation system is basically a linear or non-linear system. So what is basically a accumulation system? First of all, we have to see. So basically accumulation system is basically a, we define for discrete time signal. Okay, so here output y of t is defined as summation, oh sorry, y of n. This should be y of n. K is equals to minus infinite to infinite x of n, x of k. Okay, so here we have to check whether this system is basically a linear or non-linear system. So as I said in the previous class, to check whether a system is a linear or not, what we will do, we will check whether this system is basically following this homogeneity and scaling property, additivity. So if a system is following both homogeneity and additivity property, so we can say that this system is a linear system. Okay, so like here, if suppose this is my system 1, okay, where I am applying this input x1 of n, so at the output what we are getting, y1n which is equals to summation k is equals to minus infinite to infinite x1 of n. Okay, so now if we have the another system where we are applying another input signal x2n, so at the output what we are getting y2n is equals to summation k is equals to minus infinite to infinite x2 of n. Okay, so if suppose I am applying a new signal x of n, let us say it's x3n is equals to alpha x1n plus beta x2n. Okay, so what will be the output then? So output y3n is defined as summation k is equals to minus infinite to infinite x3n. Okay, so now place the value of x3n here. This will be equals to minus infinite to infinite alpha x1n plus beta x2n. So now we can distribute this summation inside this. So what we will get here, alpha summation k is equals to minus infinite to infinite. I am sorry, this will be k. This will be k here. Okay, so this is equals to alpha x1 of k plus beta summation k is equals to minus infinite to infinite x2 of k. So here from here we can say that this value is equals to basically y1 of n, and this is equals to y2 of n. Okay, so this will be equals to alpha x y1 of n plus beta y2 of n. Okay, so if we are applying this kind of signal at the input of this system, okay, and we are getting the same response at the output, so this kind of system is basically a linear system. Okay, so this accumulation system is basically a linear system. So I hope this problem will be clear to you. So if you have any doubt, then please ask. Any doubt? Okay then. So now moving ahead. So what is basically a linear time invariant system? Okay. So a linear time invariant system is basically an abbreviation of linear and time invariant. Okay. So in short, it is also known as LTI system. Okay. So LTI system is basically an important class of system that satisfy both the linearity and the time invariance property of the system. Okay. So in the previous class, we have seen that these properties individually how to check. Okay, if a system is given to you, so how to check whether it's a linear system, it's a time invariant system, so those all we have seen in the previous class. So in this class we introduce a new kind of system which is basically a LTI system, which satisfy both the linearity and time invariance property. Okay, so it's a basically a special kind of system. So if a continuous time system that satisfies this property is called as linear time invariant continuous time system. Okay, so if suppose you have a continuous time system, okay, so this is a continuous time system where you are applying input x of t. Okay, so this system is known as LTIC system because it's a continuous time system. Okay, so basically in any system the objective is to determine that what will be the output of this system. If we are applying a specific input to the system, then what will be the value of output here. So this is basically our target. So okay, so basically the input output relationship of any LTI system is basically described by using a linear differential equation. Okay, so the input output relationship that a LTI system is following is basically is described by this linear differential equation. Okay, so this linear differential equation is of the form like this. Okay, so here d raised to the power n by dt and y. So here y is basically the output. Okay, so from here we can see that this is basically a differential equation. Okay, in the decreasing order. Okay, and here these a n minus 1, a n, a naught, so these are basically a constant coefficients. Okay, similarly at the inputs, for the input side there will be a differential equation. Okay, of the form bm dm by dt m x plus bm minus 1 dm minus 1 by dt m minus 1 x plus dot 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 plus b1 dx by dt plus b naught x. Okay, so any input output relationship of any LTI system is described by using this linear differential equation. Okay, so by solving this linear differential equation we can easily obtain that what is the output of this system, because input is known to you, and if input is known to you, by using this relationship between input and output and solving it by using mathematics, okay, we can easily obtain that what will be the output of this system. So now moving ahead, I am taking an example here which is basically a RLC circuit, and try to show you that how to achieve this input output relationship, how to how to obtain the differential equation here. Okay, to show the input output relationship between the input applied to the system and the output that is obtained across any uh, across the load side. Okay, so let us suppose this is a RLC system. Okay, at the input I am applying uh, the source which is x of t here. Okay, so here we have to show the relationship between xt v of t, then we have to show the relationship between xt and w of t, and at last we have to see relationship between xt and y of t. So here vt is basically a voltage that is obtained across this inductor, whereas wt is basically a voltage that is obtained across this capacitor, and y of t is the voltage that is obtained across this resistor once we apply this voltage source x of t at the input side of this system. Okay, so this is basically a system only. This is basically a system only. So once we applied this input to the system, uh, how the output will behave across any element, circuit element, that is our objective to analyze it. Okay, so I hope this problem is clear to you. So now moving ahead, so to solve the input output relationship between input applied to the this RLC system and output across any element, what we will do, we will first apply Kirchhoff voltage law here. Okay, so first I am applying a Kirchhoff voltage law. So across this loop we will apply the KVL. So x of t is equals to L di by dt plus Ri. Okay, means the R into I, that is current flowing through this resistor, is equals to the voltage y of t. Okay, plus voltage across capacitor which is equals to 1 over c integral minus infinite to t it dot dt. So this is basically a KVL that is applied across this loop. Okay, so from here we can see that it contains both the differential as well as integral operator. So to make and so eliminate this integral operator, what we will do, we will take differentiation at both the side with respect to time here. So like here we can see that I already take derivative here. So this becomes L d square I by dt square plus R di by dt plus 1 over C I t is equals to dx by dt. So this basically represents the input output relationship. Okay, so not input output relationship, basically here it represents the relationship between input applied to this system and current flowing through this system. So now we can move ahead and see that how to analyze relationship between input and, first of all, voltage across this inductor, that is V of t. Okay, so we first analyze the relationship between xt and vt. Okay, so for any inductor that is carrying current I, okay, so the voltage across this inductor, we know that it is represented as V is equals to L di by dt. Okay, so now in this equation current is known. Okay, and we have to basically make a relationship between the input applied, that is x, and v. So what we will do here, we will take integration here. So at both the side we will integrate with respect to time. So what we will get, I is equals to 1 over L integral v dot dt. Okay, so once you know the value of I here, so we can easily replace this I in this equation. So what we will get, dv by dt plus 1 plus r over L vt plus 1 over lc integral vt dot dt is equal to dx by dt. So here also we can see that it contains both differential and integral operator. So we can take one more derivative at both the side. So this becomes equals to d square v by dt square plus r over L dv by dt plus 1 over lc v is equals to d square x by dt square. So see, here we derived basically the relationship between input applied and voltage across this inductor, which is basically our target. Okay, so that's how we can represent the input output relationship of any LTI system by using this kind of differential equation. We can easily derive it. Okay, similarly, we can easily derive the relationship between input applied and the voltage across this capacitor. So let us see that uh, how to obtain a relationship between the input applied to this system and the voltage that is obtained across this capacitor. So for a capacitor which carrying a current I, okay, so the voltage across this capacitor, we can easily say that this Vc is equal to 1 over C integral I dot dt. Okay, so here also I is known to us. Okay, so if we make a relationship between I and Vc, so we can directly put the value of I here so as to make a relationship between Wt and X. Okay, so here this will be Wc basically. Yeah, this will be W. Okay, so for that what I do here, I take a derivative at both the side is equal to 1 over C I. So I can be denoted as C dWc over dt. So now I directly put the value of I from this equation to here in this equation. Okay, so once I put the value of I, So finally we get this equation, that is LC d cube W by dt cube plus RC d square W by dt square plus dW by dt is equal to dx by dt. So this is the final differential equation. So see, we can integrate this equation at both the side with respect to time. So we will eliminate basically one differential operator, otherwise uh, it contains three root. Okay, it contains three root. So to eliminate one, what we will do, we will integrate both side with respect to time. So once you integrate, you will get this equation, that is LC d square W by dt square plus RC dW by dt plus W is equal to x. So this is the final differential equation which shows the relationship between the input applied to this system and the output voltage that is obtained across the capacitor. So that's how basically I am trying to show you that by using this procedure basically I we can uh, we can obtain a relationship between the input applied to any system and the response that is obtained at the output of the system. Okay, so I hope this is clear to you. So now moving ahead, let us take an example. Okay, so here basically uh, what this problem states, that this is a RC circuit where the value of resistance is given to us, which is 5 ohm, and the value of capacitor is also given to us, which is equal to 1 over 20 farad. Okay, so basically we have to determine the output signal, that is y of t, when the input voltage is given as, so this xt is basically given us as sine of 2t. So this input is given to us. Based on that, we have to determine the value of output that is obtained across this resistor. Okay, so here also one initial condition is given to us, which we will use later in while solving this question. Okay, so this initial value is also providing to us. So let us move ahead and check that how to proceed, how to obtain the response of this system when the input applied to this system is sine of 2t. So we will use the same procedure here as well. So we will first apply the KVL in this loop. So once you apply the KVL in this loop, what you will get, x of t is equal to 1 over c integral it dot dt plus I into r. It means that the input applied to this system is equal to voltage across this capacitor and voltage across this resistor. Okay, so from there we got this equation. Okay, so like here it this doesn't seems like it is a differential equation. So to make this look like as a differential equation, what we will do, we will take a derivative at both the side. Okay, so once we take derivative at both the side, we will get this equation, that is dx over dt is equal to 1 over ci plus di by dt into r. Okay, so this is basically a differential equation. So now basically we have to obtain the response across this resistor. Okay, so this yt will be the output of this system and xt will be the input, which is very obvious here. Okay, so in this equation basically it shows a relationship between input applied to this system and the current flowing through this system. Now to make a relationship between xt and yt, what we will do, we will use Ohm's law. So Ohm's law states that the voltage across any resistor y of t is defined as r into I of t, that is the value of resistance multiplied by the current flowing through this resistance. Okay, so from here we can say that it will be equals to y of t over r. Okay, so now we got the value of current that is flowing through this loop. So we will put this value of I of t here. So the final equation that we will got here is given like this. You have to just replace the value of it here. Okay, so this will be equals to dx over dt is equals to d by dt of y plus 1 over rc into y of t. So this is basically a differential equation that shows a relationship between the output across the resistor and the input applied to the system. Okay, so once you got this differential equation, so now our next target is to obtain a relationship, obtain a final response uh, that is yt here. Okay, once we applied the input which is equals to sine of 2t. Okay, so for that what we will do, we will now put here the value of xt which is known to us, which is sine of 2t here, and the value of r and c which is given in the question. So r is equals to 5 ohm and c is equals to 1 over 20 farad. So once you put this value here, so the final differential equation that you got here is equals to dy by dt plus 4yt is equals to 2 cos of 2t. So this is basically the final differential equation that we have to use and determine the value of output voltage across this resistor. Okay, so now how the question is how to solve this differential equation. So for this question, basically, as we have not covered the Laplace equation for solving the circuit. Okay, so what I will do here, I am using the basic mathematical tool. Okay, not tool, basically the basic mathematics concept, so as to solve the differential equation. So the mathematics says that if you have a differential equation, so the output of this differential equation yt is expressed basically as a sum of two components. One is the zero input response, the another one is the zero state response. So the total output is basically a summation of zero input response and zero state response. So let us take a look that what is this zero input response and zero state response here. So zero input response, as the name suggests, here we does not provide any input to the system. So basically we are analyzing the system that is produced by the initial condition. Okay, so initial condition means if suppose this is the system, let us say it's a capacitor only. Okay, so as we all know that once you uh, initially this capacitor is charged, let us say, okay, with a voltage v naught. Okay, so this act as a initial condition here. So so what we will do, we will check the response here, that is y z I. Okay, once we does not provide any input here, so we check that what will be the value of output due to the initial condition of the system here. So this response is basically known as the zero input response, and sometimes it's also known as the natural response because we are not providing here any input. This basically we are analyzing based on the initial condition that is already system have. Okay, we are not externally providing here any kind of input. So based on the initial condition we are analyzing that what will be the output here. So this is known as zero input response or natural response. Whereas the second response, that is zero state response. Okay, so here we are providing the external input and we are assuming that there will not be any initial condition that the system have. So this response basically produced due to the input applied to the system. This does not depend on the initial value of the system. Okay, so this response is known as the zero state response. Okay, and sometimes it's also known as the forced response. Okay, because here we are forcing the input to the system. Okay, we are forcing to the input to the system, and then we are analyzing that what will be the response of the system, that is yzs. Okay, so the total response is basically a sum of these two response. So what we will do here for solving this differential equation, we will we will check these response individually, and in the last what we will do, we will combine this response. Okay, so let us see that how to obtain this response individually. So our first target is to determine the zero input response to the system. Okay, so like here, this is basically our input, so we have to put this input as a zero. Okay, if xt here will be 0, so the whole term will be 0. So the total differential equation is denoted as dy by dt plus 4y of t is equals to 0 here. So this is my differential equation for zero input response. Okay, so that's why I'm writing it like this. So now, as this differential equation is a first order differential equation, so it contains only a single root. Okay, so the response of this kind of differential equation is given by this, that is a e raised to the power, that is a e raised to the power minus mt. Okay, where m is the value of root. Okay, so here if we will solve, so s will be equals to minus 4. So minus 4 is basically the root of this differential equation, so that's why I put m as minus 4 here, m as 4 here. Okay, so basically this will be plus mt. So once you put m is equals to minus 4, the so the input zero input response yzit is defined as a e raised to the power minus 4t. So this is basically my zero input response. So now here a is basically a constant. So for determining the value of a here, what we will do, we will use this initial condition that is given to us. Okay, so by using this initial condition, we will determine the value of a here. So now put the value of initial condition, that is when we put t is equals to 0 minus, so the value of y will be 2. Okay, so once you put the value of t here as a 0, okay, so what you will obtain, a is equals to 2. So now you can put the value of a here as 2. So the total response y z I t is defined as 2 e raised to the power minus 4t. So this is basically the total uh, zero input response. Okay, due to the initial condition that is present in the system itself. Okay, so this is basically the zero input response. Okay, so now we obtained the zero input response. So our next task is to determine the zero state response here. Okay, so for obtaining the zero state response, what what we will do, basically zero state response means you are applying input to the system, and then you are analyzing what will be the output of this system. Okay, so the output of zero state response contains two terms. One is the homogeneous component, the other one is the particular component. So the output of this zero state response is basically a summation of homogeneous component, and the second one is the particular component. Okay, so the homogeneous component of zero state response will almost similar to the zero input response. Okay, so y of ZS, that is zero state response for homogeneous component, is equals to define as C e raised to the power minus 40. Okay, so that is how we can determine the homogeneous component, whereas for determining the particular component, due to the uh, applied input, that is xt is equals to sine of 2t. Once you put the value of xt here, so the zero state response, sorry, the particular component of the zero state response is defined as k1 cos of 2t plus k2 sine of 2t. Okay, so if you are unable to get it, I urge you to go to the mathematics, engineering mathematics course, and check that how to determine the zero state response and zero input response of any differential equation, because it's a very basic. Okay, so if you are unable to get it, I urge you to go and check engineering mathematics differential equation. From there you will get the same process, so as to determine the homogeneous component, particular component. Okay, so here I am just providing the application, that how to apply all those concept here, so to solve any differential equation. Okay, so once you get the homogeneous component and the particular component of the zero state response, uh, what you have to do, like here c is constant, k1 is constant, k2 is constant. Okay, so how to determine it? So basically for determining this, what we will do, first of all we will put this particular component of this zero state response in this differential equation, which is our main differential equation. Okay, that is dy by dt plus 4yt is equals to 2 cos of 2t. Okay, from there we can determine the value of k1 and k2. So let us see. Here the differential equation is dy by dt plus 4y is equals to 2 cos of 2t. Okay, so now put the value of y that we have obtained here like this. Okay, so this is equals to k1 minus sine of 2t, and 2 will be take outside here, plus 2k2 cos of 2t plus 4k1 cos of 2t plus 4k2 sine of 2t is equals to, yeah, this will be equals to 2 cos of 2t. Okay, so from here we can take this constant common as minus 2k1 plus 4k2 into sine of 2t plus 2k2 plus 4k1 into cos of 2t is equals to 2 cos of 2t. So now we can compare at both the side the coefficient. So this is equals to minus 2k1 plus 4k2 is equals to 0. This is my first equation, whereas 2k2 plus 4k1 will be equals to 2. This is my second equation. So now from the first equation we can say that 2k1 is equals to 4k2. Okay, so we can put the value of 2k1, or say k1 is equals to 2k2. So from here we can put the value of k1 in this equation. So this is equals to 2k2 plus 8k2 is equals to 2. So the value of k2 is equals to 0.2. And once you get the value of k2, the value of k1 is defined as 0.4. So that is how we can determine the value of k1 and k2. So once we know the value of k1 and k2 here, we have to just put the value of k1 and k2 in this response, that is zero state response. Y z s t is equals to homogeneous component plus particular component. Okay, so here we are basically taking a summation of these two components. So now what we will do, so basically, as I said earlier, that in case of zero state response, we are consider that there will not be any initial condition that is present in the system. We are basically applying the input to the system, and then we are checking that what will be the output. So here there will not be any initial condition present in this system. Okay, so considering this, that there will not be any initial condition, so at t is equals to 0, the value of y of t will be equals to 0. So that we will put here. So uh, let me erase this. Yeah, so what we will do, we will put this condition to this zero state response. So this will be equals to 0 is equals to c plus this term will be 0 because sine term is there, then 0.4. Okay, so from here we get the value of c as minus 0.4. So now we can put the value of c as minus 0.4. So yzs will be equals to minus 0.4 e raised to the power minus 4t plus 0.2 sine of 2t plus 0.4 cos of 2t. So the total response is defined as 0 input response plus 0 state response. So now we will take a summation of these two response that we obtained individually. So this is equals to 2 e raised to the power minus 4t plus, oh sorry, this will be minus 0.4 e raised to the power minus 4t plus 0.2 sine of 2t plus 0.4 cos of 2t. So this will be equals to 1.6 e raised to the power minus 4t plus 0.2 sine of 2t and plus 0.4 cos of 2t. So this is the total response of the system due to the input applied, which is equals to, yeah, sine of 2t. So that's how we can determine the response of any system once input is given to us and also circuit parameter is given to us. So I hope this problem is pretty much clear to you, and if you have any further doubt then please ask. Any doubt? Okay, so let us move ahead. So the next topic is impulse response of the system. Okay, so let us see that what is a impulse response of any system. So basically in the previous slide we have seen that input output relationship is basically we can determine based on the differential equation. Okay, but there is an alternative way for representing the input output relationship of any linear time invariant system, which is known as the impulse response of the system. Okay, and it is denoted by a symbol h of t. Okay, so as the name suggests, this is the response of the LTI system. So if suppose this is the LTI system, okay, so it is the response of the system once you apply the impulse at the input of the system. Okay, so once you provide input as an impulse to this linear time invariant continuous time system, so whatever the response that you obtained at the output, so this is known as basically an impulse response of the system. Okay, so sometimes we also denoted it like this. So here del t is basically applying at the input, and at the output what we are achieving, that is h of t. Okay, so this is how we can show the basically the input output relationship. Okay, so as this is a linear time invariant continuous time system, so it satisfies both the linearity as well as time shifting property, as we all know. So if suppose uh, you are providing any scaling and time shifting at the input side, which is basically a uh, impulse signal. Okay, so like here we can see that we are providing scaling like a and time shifting as t minus t naught at the input side. So at the output side we are also achieving the same thing, means at by the same factor it is scaled, by the same time shift it is basically shifting. So if you are applying a signal which is denoted as a delta of t minus t naught, so at the output you will achieve the same thing, means scaling factor will remains the same, that is a, and the shifting the time by which you are shifting basically the input delta signal, with the same time you are shifting the output, that is h of t minus t naught. So I hope this theory is clear to you. So let us move ahead and see some numericals based on this. So our first problem is calculate the impulse response of the following system. Okay, so here y of t is defined as x of t minus 1 plus 2x of t minus 3. Okay, so first of all, if suppose any system is given to us, so what we will do, we will check whether this is basically a linear and time invariant system or not. We have to check whether it's a linear and time invariant or not. If it satisfy both the linearity and time invariance property, then what we will do, we will do that we will replace the input x of t by del t and output y of t by h of t directly. This basically shows our impulse response of the system. So it means that we have to first check the linearity and time invariance property of any system, and if it satisfy both linearity as well as time invariance property, then what we will do, we will replace x by del and y by h, and the response that we will obtain is basically, we can say that it is basically a uh, impulse response of the system. Okay, so from here you can check basically whether this system is linear and time invariance or not. I'm just stating here that it is a linear and time invariant system. Okay, you can later check by yourself, but I am basically here saying that it is a linear and time invariant system. So if it is a linear and time invariant system, what I will do, I will replace y of t by h of t and x of t by delta of t. So once you replace these parameters here, you will get h of t is equals to del of t minus 1 plus 2 del of t minus 3. Okay, so this represents basically the impulse response of the system. Similarly, in the second problem, like we have to determine here the impulse response Okay, so for that, what we will do, we will first check these conditions. Okay, so later you can check this linear and time invariance property for this system as well, and you will definitely get that it is a linear and time invariant system. Okay, so once you get this system is satisfying this linearity and time invariance property, so what you will do, you will just replace x of t as del of t and y of t as h of t. So after replacing this parameter, you will get dh by dt plus 4ht is equals to 2 del t. Okay, so this is basically a differential equation. Okay, so here basically we have to obtain the impulse response, not the relation. So we have to further solve this question so as to obtain the h of t. Okay, so for that, what we will do, if we already know the Laplace, that how to apply the Laplace for solving this kind of differential equation, that it will be very easy for us. But for now, as the Laplace is not covered till now, so we will use the basic mathematics so as to solve this differential equation. Okay, so the basic mathematic states that for the first order differential equation having this form, that is dy by dt plus ft into yt is equals to rt. So for solving this numeric this kind of differential equation, uh, the uh, uh, the output means the response of this differential equation yt is defined as e raised to the power minus p integral e raised to the power p r dot dt plus c. So here p is basically a function which we can obtain by using this equation, and r is basically a input applied to this system. Okay, and c is a constant parameter. Okay, so as our this differential equation is uh, looking same as this one, so we will use this property so as to determine the solution of this differential equation. Okay, so first of all, we are solving for p parameter. Pt is equals to integral of ft. So ft, from here we can say that it will be equals to 4. So this pt is equals to integral 4 dot dt, and this will be equals to 4t. So the value of pt will be equals to 4t. Okay, so now once you determine the value of pt, we can directly substitute the value of pt in this equation for determining the value of output, or say response of this differential equation. Okay, so here the response is basically the ht. So ht is defined as e raised to the power minus p. So this p is basically a 4t. So this will be equals to e raised to the power 4t into 2 integral e raised to the power 4t del t dot dt plus c. Okay, so I am just uh, putting the value of r, which is input to this system, and here for this question, this is basically an impulse. Okay, and yeah, this p value we have already calculated, this will be equal to 4t. Okay, so once you replace all this parameter here and solve it, so you will get h of t as 2 e raised to the power minus 4t ut plus c e raised to the power minus 4t. Okay, so now for determining the value of ht, we have to determine the value of this constant c here. So for that, we will use the zero initial condition. So zero initial condition states that for t is equals to 0 minus, means if this is the time axis and here this is basically a t is equals to 0. So for t is equals to 0 minus, just before this t is equals to 0, the response will be 0 here. The response will be 0 here. So this is the response, so this will be 0 here. Okay, so I am using this property. So by using this property we can determine that C will be 0 here. So the total input response of this system is given as h of t is equal to 2 e raised to the power minus 40 into ut. So that's how you can determine the value of uh, that's how you can determine the response of any differential equation. Okay, so basically I am using here the basic mathematics, or say mathematics, for solving this first order differential equation. But later, once we covered the uh, Laplace equation, then it will be very easy for us to solve such kind of differential equation. No need to remember all these kind of uh, yeah, theorems so as to solve the differential equation. So later we will also see the Laplace equation for solving any circuit. Okay, so I hope this problem will be clear to you, and if you have any doubt then please ask. Okay, so moving ahead, Uh, yeah. So the next problem is the impulse response of an LTIC system is given by h of t is equal to e raised to the power minus 3t into ut. So basically we have to determine the output of the system for the input signal x of t is equal to del of t plus 1, del of t minus 2, sorry, 3 del of t minus 2 plus 2 del of t minus 6. Okay, so due to this input signal, what will be the output of this system, that we have to analyze. Okay, so like here we can see that the input is basically a summation of different impulse, basically different shifted impulse here. Okay, so as we all know that this LTIC is basically satisfying the linearity as well as time shifting property. Means if you are shifting the input signal by some parameter, let us say T naught. Okay, so at the output as well you will shift the output by the same parameter which is equal to T naught. Okay, so as the input here is del, okay, which is a delta signal. So for del of t plus 1, the output will be h of t plus 1. Okay, if you are shifting the input signal by some parameter, the same shift you will observe at the output of the uh, system. Similarly, for input signal which is equal to 3 delta of t minus 2, the output will be equal to 3 h of t minus 2. And for the third signal which is equal to 2 delta of t minus 6, the output will be equal to 2 h of t minus 6. So now what we will do, we will take a superposition of uh, these three signal, because they are basically uh, satisfying the linearity property, because system is basically satisfying the linearity property. That's why we will take the summation of output that is obtained from individual input signal. Okay, so that's how the total output that is obtained from the system, which is equals to the response obtained from individual input signal. So here yt will be equals to h of t plus 1 plus 3 h of t minus 2 plus 2 h of t minus 6. So as h of t is given to you, so you can put the value of h here. So the total yt will be equals to e raised to the power minus 3 t plus 1. Okay, so this basically start from t plus 1 plus 3 e raised to the power minus 3 t minus 2 u of t minus 2 plus 2 e raised to the power minus 3 t minus 6 and u of t minus 6. So this is the total response that is obtained from the LTIC system. So I hope this problem is clear to you. So now moving ahead, so till now we have seen that uh, what will be the output of the system, what will be the output of the system once we apply input as impulse signal. So now the next question is, what happened if we apply a specific signal at the input of this system? So what will be the output of this system? Okay, so here basically uh, we are proceeding that how to determine the response of the system for an arbitrary applied input. Okay, so for determining the output of the system for any arbitrary applied input, what we will do basically here, we consider the input signal as a linear combination of scale and time shifted impulse function. Okay, so the input signal that we are applying, we have to consider it like this input signal is a linear combination of scale and time shifted impulse function. Okay, so the output of this linear combination of scale and time shifted impulse function is basically defined as the summation of response obtained from the individual shifted impulse. Okay, so you have to basically calculate the response of this system for each individual impulse, means shifted impulse, and then take the summation of the response so as to obtain the total response of this system. Okay, so that's how we can calculate basically the output of any system for a specific input that is applied to the system. Okay, so in other words, we can say that if the input signal is xt is passes through a linear time invariant system with impulse response h of t, the resulting output y of t of the system is calculated by convolving the input signal and the impulse response. So if this statement says that if you know the impulse response of the system and you also know that what is basically the input applied to this system, so the output of this system is basically a convolution of this input applied to the system and the impulse response of the system. Okay, and this can be calculated as minus infinite to infinite x of tau into h of t minus tau dot d tau. So this is basically a convolution. I'm sorry. Yeah, so this is basically representing the convolution of uh, convolution of input applied to this system and impulse response of the system. Okay, so I hope this convolution part is clear to you. So now moving ahead, and we will check uh, that how to apply this concept of convolution so as to determine the output response of any linear time invariant continuous system. Okay, so here the input signal that is given to us is xt is equals to e raised to the power minus t into ut, and the impulse response of the system is given as e raised to the power minus 2t into ut. So now based on that, we have to determine the output response of the linear time invariant system. Okay, so to determine the output response of this linear time invariant system, we will use this convolution property. Okay, so here the x of t that I am considering is equals to e raised to the power minus t into ut, whereas h of t is equals to e raised to the power minus 2t into ut. So now y of t is defined as minus infinite to infinite x of tau h of t minus tau dot d tau. Okay, so we have to put the value of x and h here, minus infinite to infinite, e raised to the power minus tau, okay, into u of tau into e raised to the power minus 2t minus tau into u t minus tau dot d tau. Okay, yeah, so once you put this value here, you will get, you can solve this. Okay, so like here u of t can be given as 0 to infinite, because u will start from 0 and go till infinite, so that's why starting limit is start from 0. Okay, e raised to the power minus tau into e raised to the power minus 2t into e raised to the power minus 2, this will be plus 2 tau. Okay, u of t minus tau dot d tau. Okay, this, from here we can take this e raised to the power minus 2t as a common, minus 2t e raised to the power. Okay, this basically this unit impulse basically change the limit of this integral from 0 to t, and this will be equals to minus uh, yeah, this will be equals to plus tau dot d tau. Okay, so this we can further solve, like e raised to the power minus 2t into e raised to the power tau limit 0 to t. So from here we can get e raised to the power t minus 1, and this will be equals to minus t minus e raised to the power minus 2t. So this basically represents, yeah, so this basically represents the convolution of uh, sorry, so this basically represents the output of the system. Okay, so that's how we can apply this concept so as to determine the output of uh, any system, okay, by using convolution theorem. So now we are going to see some of the most important property of this linear time invariant continuous time system. Okay, so first property is memory linear time invariant continuous system. So a continuous time system is said to be memoryless if the output yt at any time t is equal to t naught depends only on the value of applied input xt at the same time instant. Okay, means uh, uh, means that if you are applying input to the system at time instant t is equal to t naught, so at the same time you will observe the output to the system. Okay, it will not depend on the future value, it will not depend on the past value, it will only depend on the value of the input applied at the same time. So this is known as memoryless system. Okay, so this kind of memoryless system, the input output relationship is of the form y is equal to k into x of t. Okay, so this kind of relationship is basically defined the memoryless system. Okay, so if your input applied is basically equals to delta of t, means if your input is same as the impulse response, so the output is basically the impulse response of the system, that is h of t is equal to k into del of t. Okay, so from here we get a conclusion that a linear time invariant system is basically a memoryless system if and only if its impulse response h of t is equal to 0 for all, for the t which is not equal to 0, means like impulse is basically defined at t is equal to 0. So apart from this t is equal to 0, impulse response will be 0. So this is basically the conclusion of this uh, memoryless linear time invariant system. Okay, so we will see some numericals on in the future slide. So by using basically this condition, we will try to check whether the system is basically a memoryless system or it is a with memory system. Okay, similarly the second property is the causal linear time invariant system. Okay, so a system is said to be causal if the output at any time t is equal to t naught depends only on the value applied uh, input signal at and before the time instant t is equal to t naught. Means a linear time invariant system is said to be causal if it depends basically on the past value and the current value, okay, of the input applied. It will not depend on the future value. So such kind of system is known as causal linear time invariant continuous system. Okay, so like uh, we know that if this input is given to you, that is x, and impulse response is also given to you, so by using this convolution property we can determine that what will be the output. And if suppose we are try to determine the output of the system for any given time period, for any given time, let us say this t is equal to t naught. So y of t naught is given as minus infinite to infinite x of tau into h of t minus tau dot d tau. Okay, so now uh, yeah, so for a causal system, the output must not depend on the input for tau greater than t naught. It means, so like, let us say this is my input signal x of t, okay, and this is applied for t up to t is equal to t naught, okay. So the output, okay, output y of t for t greater than t naught, it basically does not depends on the value of uh, future value. Basically it depends only on the applied input at t is equal to t naught or the previous value, then only it will be a causal system. Okay, so this condition is only satisfy if the time shifted and reflected impulse response will be 0 for t greater than t naught. Okay, so we are choosing a special case where t naught is equal to 0. So under this case, h of minus tau will be 0 for tau greater than 0. Okay, so from here we will get a conclusion that h of tau will be 0 for tau less than 0. Okay, so by using this condition we can check that whether a given system is a causal or not. Okay, similarly a stable linear time invariant system is a Bibo stable if for an arbitrary input, for an arbitrary bounded input, the system produces basically an bounded output signal. Okay, so if suppose xt is our input signal, which is a bounded input signal, okay, and you are applied this input to a linear time invariant system with impulse response h of t, so the magnitude of output basically is defined as mod of yt is equal to minus infinite to infinite h of tau x of t minus tau dot d tau. Okay, so this x of t basically a bounded input. Okay, so that's why we will take it as a common here. Okay, so this will be bx integral minus infinite to infinite mod of h of tau dot d tau. Okay, so from here we can say that if the value of this integral is finite, okay, then only this output will be finite, and then we can say that this system is a Bibo stable system. Otherwise this is not a Bibo stable system. Okay, so considering this, we come at the outcome that if the system is satisfying, the impulse response of any system is satisfying this condition, then we can say that it is a stable linear time invariant continuous system. So let us move ahead and see some problem based on that. So first here is the problem which where we have to determine whether the impulse response that is given to us is a memoryless, causal, and stable or not. Okay, so based on the properties that we have seen earlier, okay, on the basis of that, here we have to check whether it's a memoryless, it's a causal, or it's a stable system. Okay, so let us see one by one. So first system is ht is equals to del t minus del of t minus 2. Okay, so first system is h of t is equals to del t minus del of t minus 2. Yeah, so yeah, so this is the first system impulse response of any system given to us. So first of all, we have to check for memoryless property. Okay, so memoryless property states that h of tau h of tau here, this will be 0. Actually this is incorrect. Here this h of tau will be 0 for t is not equals to 0. Okay, so from here if we see that at t is equals to 0, h of 0 is equals to del of 0 minus del of t minus sorry minus 2. Okay, so basically this depends on the past value. So we can say that this is not a memoryless system. Okay, this is not a memoryless system. Okay, so now we will check for the causality property. Okay, so from here we can see that h of t basically depends on the current value of input applied and the past value of input applied. So that's why it is a causal system. Okay, it is a causal system because causal system in the causal system, the output of the system only depends on the current input applied and the past value of input applied. So that's why it is a causal system, because here as well the input applied is the out impulse response is basically depend on the current value of input applied and the past value of input applied. So that's why it's a causal in nature. Similarly, for stability property, what we have to check whether this integral minus infinite to infinite mod of h of t is is a finite value or not. Okay, so here we put the value of h of t, okay, which is equals to mod of del of t minus del of t minus 2. Okay, so here once you put the value of mod, so this will be equals to minus infinite to infinite mod of del of t, mm, mm, yeah, plus dot dt minus infinite to infinite, this will be minus del of t minus 2 dot dt. Okay, so once you solve this, you will get this will be equals to 1 plus 1, which is equals to 2. Okay, so this shows that it is a finite value, that's why this system is a stable system. Okay, so that's how we can uh, use the uh, conclusion of these properties, that is the memoryless, uh, causality property and stability property, so as to check whether a given system is a memoryless, causal system, stable system or not. Okay, so yeah, The second system is, we have to check, yeah, 2 rect of t minus t by 2. So the second system is basically 2 rect of t by 2. This is our second system, impulse response of the second system. Okay, so see, the standard rectangle system is defined as a rect t by tau. Okay, so the amplitude of this rectangle is defined as a. This tau is basically minus t by tau to t by tau. Okay, so that's how a standard rectangle signal is basically represented. So now here we can see that that as h of t is not 0 for t not equals to 0, so that's why it is not a memoryless system. Okay, so now if we check for the causality property, so we can see here that it's depend on the future value as well. So that's why it is a non-causal. Okay, so if uh, we check for stability property, we have to check this condition, that is minus infinite to infinite mod of h of t dot dt. So once you evaluate this integral, this will be equals to 4, which is a basically a finite value. Okay, so this shows that this system is basically a stable system. Okay, so that's how we can determine whether a given system is a memoryless, it's a causal, and it's a stable system or not. So now similarly we can evaluate whether this third system is a memoryless, causal, or stable or not. So this third system is given as, yeah, 2 e raised to the power minus 4t into u of t. Okay, this is the third system that is given to us. Okay, so like if we plot this system, so this look like this will be 2. Okay, h3t, this will be equal to h3t. Okay, so from here we can see that uh, it depend on the future value. Okay, so that's why it is not a memoryless system. Okay, whereas if we check for causality, so it does not depend on the future and past value, it depends on the future value. Oh, sorry, it does not depend on the current value and the past value, it depends on the future value. So that's why it is a, okay, sorry, so like for causality we have to check whether h of t is equals to 0 for t less than 0 or not. So from here we can see that this h of t is equals to 0 for all t less than 0. Okay, so that's why it is a causal system. Similarly we can evaluate this integral so as to check whether this value is finite or not. So once you calculate, this will be equals to zero point 0.5, which is a finite value. So that's how we can say that it is a stable system. So by using these conclusions, that integral minus infinite to infinite mod of h of t dot d tau dt is less than infinite, means it's a finite value. So it shows that it's a Bibo stable. Similarly, if h of t is equal to 0 for t less than 0, then it is basically a causal system. And if h of t is equal to 0 for all t not equals to 0, then it will be a memoryless system. So by using these conclusions, we can determine whether a system is memoryless, causal, or stable or not.